After that's graded, I'll upload your Canvas with your module exam points, and your finals next Wednesday, right? Is that correct? Okay, so it will be in this room starting at 12:40 or 10:45 a.m. So you have 110 minutes to do that. So the exam will end at 12:35. Again, you'll get a seat assignment that'll be posted in Canvas. I'll put up your ID, a row and seat number. I'll have like a little chart that shows you where the seats are basically. And then once you get your exam, I'll go through with the photo roster to make sure that it's you sitting in that chair and not your friend who you're paying to take the final for. As you can see, only about a third of the class shows up, so I have no idea who those other people are, and we need to have some exam security. Those exams are graded by someone else, so once they're graded, I'll upload your point total into Canvas, and then I'll take your module exams, your final exam, and I'll upload the total points you've earned for the course into Canvas. Unfortunately, I can't upload your grade because that's not allowed. So your final grade is only uploaded into SOAR, but you'll be able to figure out what it is based on your number of points. Any questions? So as you can see from the slide deck, there's 80-something slides. We're definitely not going to get through it all today. We'll get through as much as we can. The stuff that we don't finish, you'll have to go through on your own. But I have screencasts and videos on YouTube for those topics that we won't have time for. So we had left off on addition reactions. So again, we used radical CH substitution to put a leaving group into the carbon backbone. We've learned about elimination, so beta elimination to make alkenes, and now we're using those alkenes as nucleophiles and treating with different electrophiles. And of those mechanisms, there's the issue of regiochemistry, so what atom of the alkene gets what atom of the electrophile. There's concerns about the timing. Do both elements of the electrophile add at once, or is it separate steps? And then the face of the alkene. Does one atom add from the top, one from the bottom, or are they both from the top? So as you read and do more of these problems, start thinking about those concepts as well, because ultimately that can result in the production of stereoisomers. So the next reaction we're going to start with is, I think we ended on it, but we'll start with it, hydrohalogenation, and that's using these mineral acids of the form HX. So in general, HX, where X is halogen, we know that the halogen is electronegative because it has 3 lone pairs. The proton's electropositive. So the first thing that happens is a proton transfer. So the alkene is, in a sense, acting as a base to abstract that proton. And that happens according to Markovnikov's rule again, because we want to generate the most stable carbocation, and then that is trapped by X minus. So in this case, let me draw in that hydrogen just so you can see it. What will happen is the pi bond will abstract that proton. We break the HBr bond. And depending on which carbon atom does that, we have to evaluate the carbocation. So in this case, carbon 2 is going to get that hydrogen. because that results in a tertiary carbocation. So that's tertiary, that's the most stable, and then Br can attack, Br minus. So keep in mind, at that point, the attack can happen from either the top or the bottom face of that p orbital. But in this case, the major product is the tertiary bromide. tertiary bromide. And then we'll run through some questions about to review some spectroscopy. How do we identify major versus minor? Things like uniqueness, what instrumental techniques. So the major or the minor product was secondary. And again, that's because if you protonate the other carbon, you get a secondary carbocation that's then trapped. So I've already run through this on the prior slide. I apologize for my voice. I don't do a lot of talking before I come to class, so I have to warm up a little bit here. How many unique carbons does this molecule have? Correct answer is 4. Don't get distracted by that wedge that's drawn. So that may lead you to believe that that side chain has unique carbons because it's showing that proton specifically, and then it's showing that thing as a wedge. But so I draw, when I tend to do these additions, I draw things like that, what added, and then I shove the stereochemistry back in. So you have an ethyl group there, and then you have a methyl group. But coming off that, remember there's the second H, and then that methyl. So CH2, CH3, CH2, CH3. So the methylenes are the same, those methyls are the same, so that renders it down to 4. So again, pay attention to how things are drawn. Is this molecule chiral? So is there a stereogenic center? So the answer is no. Again, don't get fooled by what that's telling you, because if you redraw it, essentially the molecule looks like this. And then you can see from that central carbon bearing the methyl group and the bromine, these ethyl side chains are the same, so therefore it's not a stereocenter. So what analytical method would be best for determining the identity of the halogen used for the reaction? I think I heard D, so mass spectrometry. So remember, bromine gives a 1-to-1 ratio of M to M plus 2. So the parent, then the parent plus 2 because of bromine 79 and bromine 81. Those naturally occurring isotopes occur in a 1-to-1 ratio. So this is the minor product. That was a secondary bromide. is that a chiral molecule? So this molecule is chiral. So remember, a stereogenic center has 4 unique substituents. So what's the name of the molecule in reviewing the CYP designations? If you look at all the responses, the sort of parent part of the name is all the same. So I'm going to just draw in the numbers for the chain. So you see that everything's 2 for the bromo, 3 for the methyl, and then the rest of the chain length is the same. So you're not discriminating the responses based on that. So then you're looking at the R or S values. So the first thing I would do is go to carbon 2 and then assign whether that's R or S. So that carbon is bearing a bromine. That's the highest atomic number, so that's going to be priority 1. If we draw in that hydrogen, it's going back. So that's priority 4. Then we have carbon and carbon. Since they're the same atomic number, we have to consider what's bonded to them. That carbon has H, carbon and carbon. This has 3 H's, so that one's going to get the second priority. So the lowest priority group's back. We determine that to be counterclockwise, so position 2 should be S. So that'll eliminate B and D. And then what about position 3? What do you think that is? It kind of looks like R in a sense, but if you look, so we're considering that carbon. It has 4 different groups: a methyl, an ethyl, and then this side chain with the bromine. The hydrogen's the lowest priority, and you want that pointing away from you. So if you were to put your eye right here and look down that axis, of the 3 carbons, that one would get priority. So 1, then 2, then 3. And so if you do that, you end up going counterclockwise, so it's going to be S. So a model kit would help you do that, or if you're able to sort of change your viewpoint, you could see that in your mind. So C is out, and then A is the correct answer. So we said S and S. So which one of the responses is the enantiomer of that? So again, all of this stuff's the same. So you're not evaluating on that. What's the definition of an enantiomer? A mirror image stereoisomer. So every CYP designation has to be the exact opposite. So this you would get choice B, 2R, 3R. If this was presented to you another way in terms of instead of the name, you were given structures as the responses. So that would be the mirror image, and then that would end up as R and R. So that was the addition of H and X. The next reaction we're going to learn is called halogenation. And so that's going to use the molecular halogens X2. Since X is the same thing, both carbon atoms are getting an X. So you don't have an issue of regiochemistry. They're both getting the same halogen. But based on the way this mechanism occurs, it's not a syn addition. So remember, syn means the same face. Because these things are not adding at the same time, the addition is called anti. You get one X adds to one face, and then the other X adds to the opposite face. The reason for that is the halogen atoms themselves are big, therefore the bond distance between them is longer when compared to the bond distance between the two carbons of the alkene. So you have this really long bond and you have a shorter alkene bond. They can't both reach up the same time. So you get one adding to one face, and then the anion will add to the other. So this is an anti-addition. Because it's anti, the timing of it is asynchronous. Meaning that the X atoms add at different times along the reaction coordinate. So using our model alkene with Br2, and then this is where, again, even though it's the last lecture, the subtlety and the reaction conditions matter. This solvent is called dichloromethane, so CH2Cl2. This is a non-participating solvent, meaning that when you look at the product, you don't see any of the elements of the solvent in the products, do you? The only thing you see is Br and Br. You don't see any other CH2Cl2 within the product. So that's going to become relevant when we look at similar conditions, but the solvent then participates. So when you look at the product distribution, you can see that when I've added these, so you have a bromine at the top to carbon to bromine. So I tend to draw that first, and then I just go back and stick in any stereochemistry that was present in the starting material. So the fact that they're on opposite faces shows the anti-addition. And then it says it's forming enantiomers. So you get these mirror images where now the carbon on top in this one's bonded to carbon 2, but over here it's bonded to carbon 3. So how do we rationalize how this Br2 is adding on different faces? So that's what I mean, the kind of trick you can use. That shows an anti-addition. And then from those two carbons, I just go back and stick in the stereochemical relationship. So the methyl group's going back, the ethyl group's coming out, hydrogen back, methyl forward. So normally, when you look at bromine, we would draw it like that, and you think, well, both bromine atoms are going to approach that alkene kind of parallel and just plunk down. But as I said, they're really big, the bond's long. So instead of them coming down like this, we're going to rotate it, and only one of them is going to come down to the alkene. So really, it's coming down at kind of an orthogonal trajectory. And when we push the arrows, I'll just draw this in blue so you can see it different. So the alkene electrons come up. That's going to form a carbon-bromine bond. We have to break the bromine-bromine bond. But then also what happens is a lone pair comes down from bromine to attack the other carbon. So if we interpret what these arrows mean, the pi bond comes up to form a bond to bromine. So a carbon-bromine bond. A lone pair from bromine comes down to form a bond to carbon. And then we break the bromine-bromine bond. So here's our central carbon-carbon bond. I'm going to stick the stereochemistry back in. There's the bromine. 1 bond, 2 bond. It still has 2 lone pairs. We've cleaved off Br minus. We've generated a negative charge, and therefore we have to balance it out by a positive charge, and that positive charge is assigned to what element? So if you run through the formal charge equation, it's going to end up on this bromine. And so now we have 2 possibilities of attack. So the bromine could attack there, or it could attack there. So maybe I'll show it just here so we can follow the arrows. So that bromine will attack that carbon. So we're going to break the carbon-bromine bond. So since that bromine was on the bottom, this one has to end up on top. We plug our stereochemistry back in. And so, as I said, you're going to get the pair of enantiomers depending on, which side the bromine atom initially adds, and then once that ring opens, what carbon gets attacked. But ultimately, you end up with the enantiomers. And then keep in mind, once you form these things, it's always good to classify the functional groups. So again, that was a secondary bromide, that was tertiary. We know through these mechanisms based on rates, when you classify things, based on the substitution patterns, they react at different rates. And then relatively speaking, when we look at the two bromines, their positional relationships to one another, not their locations on the chain, but this would be called a 1,2 dibromide. Another way of saying that in organic chemistry terms is the word vicinal. So vicinal means 1,2. Any questions? So that ion, that three-centered reactive intermediate, if we put those lone pairs in, that's called a bromonium ion. And again, the nomenclature has a historical meaning. So if we cut the name right there, onium, that tends to mean positive. So when we look at the responses here, in terms of determining the charge, we could eliminate those. And then ultimately you'll find that that's a +1 charge on bromine if you use that formal charge equation. Again, that was the group number in the periodic table minus the number of lone pairs minus 1/2 the shared electrons. So say you run the reaction, you isolate your sample, you chuck it into a polarimeter. What's the specific rotation going to be? So it's going to be 0. So again, these are enantiomers. They're produced as a racemic mixture. Remember, the word racemic is defined as a 1-to-1 ratio. If you go back to when we learned about polarimetry and stereochemistry, there were the three sort of points on our line. The pure enantiomer, the other mirror image enantiomer, and then right in the middle was racemic. And then from that value at 0 to either way, you get plus or minus, and then you have those different ratios. So that was called the enantiomeric excess. So here's a question I like to challenge students with. You have two bromines in the molecule. Remember that one bromine gives a 1-to-1 ratio. So in terms of like a percent, say that was 100%, this would be kind of similar, 97%. So it's a 1-to-1 ratio. But now you have two bromines in there. What is the parent region going to look like? So if we use some logic, we can eliminate A because we already know that bromine has two isotopes. If there's one bromine, it's going to be that 1-to-1 ratio. But now we have two. And so what you're doing is thinking of what are the combinations of those two bromines in terms of the natural isotopes that they can be. Anybody got a guess? It's going to be a triplet. So remember, one bromine will look like this. That's your M. That's your M plus 2. The height's the same. So again, what does that correspond to? That's 79 Br. This is 81 Br. So if you have two bromines in the molecule and they're both 79 labeled, that's going to get you an intensity of 1. If you have two bromines and they're both 81, that will give you an intensity of 1. But now in the middle, you have two possibilities. One is 79, the other's 81, and then you swap it, 81, 79. So the fact that that can happen twice leads you to a middle peak that's twice the intensity. So we'll write those down so you can visualize it. So they're both 79, they're both 81. So again, that's how you get twice the intensity. And if you're really into math, any math majors, minors out there, if you want to challenge the neurocircuits in your brain, so remember that chlorine was a ratio of 3:1. Bromine's nice because the ratio is 1:1. You can kind of just use some logic, but with 3:1, if you incorporate two chlorines into a molecule, those subsequent parent masses will have some pretty wild-looking intensities. Questions? So same electrophile, X2, molecular halogen, but now we're going to use a participating solvent. So either water or, pay attention, an alcohol. So you have this protic solvent, H2O, or with the alcohol, OH. Now when you look at these products, since we're using water as the participating solvent, you see some elements of water in there, right? So you're ending up with a halogen and an alcohol, and these are called halohydrins. The first step is kind of the same. The molecular halogen is the electrophile. It's going to add to one face. And then you get attacked by the solvent, which in this case is water, to do an anti-addition. So it's attacking from the opposite face. If we classify this, we have a secondary chloride and a tertiary alcohol as the major product. The minor, tertiary chloride, secondary alcohol. Yeah, we'll look at the mechanism on the next slide. So again, it's an anti-addition. So the question now really is, how do we determine where the alcohol is ending up? So do I have this? So pi bond attacks, lone pair comes down, this splits off, Cl minus. The reason the Cl minus doesn't come back to attack typically when you're running a solvent, or when you're running a reaction in solvent, that molar ratio of solvent relative to your other reagents and substrates is quite a bit. There's a lot more of that around surrounding the substrates. So this is using chlorine, so that's called a chloronium ion. And so we have a choice because the water is going to attack from the opposite face. So in the green arrow, I'll show that's the preferred path. The blue arrow is the minor. So why is that? If we think about breaking a carbon-chlorine bond and then analyzing what carbocations result, that's going to help us in the right direction. So I'll just run through both of those structures so you can see what I mean by that. So right here, what I'm going to do is in the green one, I'm going to break the carbon-chlorine bond, and then I'm going to move that plus charge to the p orbital here. And then if I classify that carbocation, I'll find it's tertiary. Now I do the same analysis for the other carbon-chlorine bond. I find that that's a secondary carbocation. So the green path is going to be the one that's preferred. So the water can then add so there's the anti-addition. And then to get to our neutral product, we just do a proton transfer. So there's our halohydrin backbone. And then the rest of the substituents. Questions? Is my slide going to be Snapchat famous here in about 30 seconds? So what pair of instrumental techniques would best inform that both the alcohol and the chlorine are present? So for halogens, we want to use mass spec. For alcohols, we want to use IR because those have the best signatures for those functional groups. So this would be D. So on your final, I think there's only, 2 or 3 spec problems. They may appear complicated to you, but if you take your time, read the question carefully, they're actually fairly straightforward. The main thing is you're counting. Count the number of signals you see, look at the responses, what are the uniqueness sets. So if we put this into practice now, we're going to use bromine as the electrophile, water as the participating solvent. So overall, when we diagnose this, this is telling us we have to form a halohydrin. Based on that information, can you eliminate any responses? We can eliminate C and D. Why? Because again, that's a participating solvent. So you have to see some of those things in the product. So in this case, OH. And then between A and B, can we eliminate one? So really what you're basing this on is the stereochemistry. What was the stereochemistry for a halohydrin reaction? So A is the result of a syn addition. B is the result of an anti. So what was the halohydrin one? So halohydrin is anti, it's B. Halogen, one face, alcohol, the other. And so what I mean by that, see this H here? So you can look at that and know that water was used as the solvent. If your product was this, you can look at that and say the solvent was methanol. Any questions? So the next reaction is called epoxidation. So what is an epoxide? So in general, it's a 3-membered ring that's an ether. So that's the basic 3 atoms you need to form an epoxide. And then any other stuff hanging off these carbons are whatever. But the 3-membered ring ether, that's called an epoxide. Epoxides can come from alkenes. And one method of doing that is using the reagent shown. This is called meta-chloroperoxybenzoic acid. It's abbreviated MCPBA. So MCPBA. And what you'll notice in it's not a carboxylic acid, it's a peroxy acid. So how is that different? That OO bond is called a peroxide bond. And so now you have overall you have 3 oxygens. You have 1 in the carbonyl, then you have these other 2. These other 2 have very different reactivities. The one that I'm showing in blue, that's the reactive one in that reagent. So this oxygen gets plunked down onto that alkene. So you have 2 carbon atoms here, right? This is an epoxide. So there's 2 carbons. The oxygen from MCPBA becomes that oxygen. So without going through the mechanism just yet, I want to draw those 2 carbons. I'm going to put in the blue oxygen. And then based on the way the mechanism happens, both carbon atoms are bonded to that oxygen, right? So that addition happens at the same time. It's synchronous and it's syn. So meaning the stereochemistry of what we started with is retained. So we just draw it in. So syn synchronous. We'll walk through the mechanism, but really the way to process this, when you're diagnosing things, you have to recognize what's the reactivity of MCPBA. It's going to take an alkene to an epoxide. That's pretty much what you have to know. So the epoxide functional group is a 3-membered ring that eliminates B and D. And we end up with an ether. So that eliminates A, so C is our correct response. So it says, how many stereoisomeric epoxides will this reaction form? How many faces of the alkene are there? So again, if we consider, I'll dot these in like green. So those are the sp2 carbons of the alkene. Based on the geometry, this carbon, that carbon, and that hydrogen all lie in a plane. That plane is flat. So there's a top and a bottom face to that plane. So that oxygen can come from the top or the bottom, and now it's going to give 2 different products. So I draw them like that. So say top, bottom, and now I'm putting in the substituents, maintaining the stereochemistry they started with. So what's the relationship of those 2 products? Are they the same? Are they enantiomers, diastereomers? So we end up with 2, and they're mirror image isomers, so they're enantiomers. So I haven't drawn them exactly as mirror images, but if you imagine, if you take this molecule, sort of rotate it on an axis that's like perpendicular to the screen, you'll get the mirror image of that. So that's one way of doing it. The other way of doing it is just going through and assigning the CYP designations to each for both molecules, and you'll see that they're exact opposites. So here's a question to consider. Look at those possible products pretty carefully. I mean, even though we've went through this, I want to illustrate a point here. So which answer is incorrect? So A is incorrect. And can you give me a reason why?
Because that carbon on the right got flipped.
So the point here is that, see this methyl group's pointing out towards us? Over here it's away. What that would imply is that the oxygen's going to add to one carbon atom, then a bond rotation can occur. That does not happen because the oxygen is adding to both carbons at the same time from the same face. So that helps prove the synchronicity of the mechanism. You have to retain the existing stereochemistry. The word that we introduced before for that was called stereo specificity. And what I mean by that is if you look at the epoxide and you slice right there, since that has to add at the same time to the same face, we can say that epoxide comes from a double bond. And then we have to retain the existing stereochemistry that we see from that epoxide. So that methyl group goes back, that one comes forward, the ethyl group comes forward. So by looking at the stereochemistry of the product, you're able to infer what the starting material geometry was. So overall, the things to remember about epoxidation, you're adding an oxygen that forms the three-membered ring, and it happens in a syn and synchronous fashion. So we'll run through the mechanism of this real quick. So I'm just going to abbreviate the aromatic ring, call it R. So I drew the peroxy acid in that conformation for a reason, because we're going to push a lot of arrows here, and normally you don't push so many at once. We're going to have this pi bond come up. That's going to form an OH bond. So we're going to form oxygen-hydrogen bond here. The electrons in this bond are going to come down. So that forms a carbon-oxygen bond. the pi electrons are going to come back up and bond to that oxygen. And then we clip the OO bond, and that forms now a new carbonyl, so C double bond O. So the epoxide is formed. We retain the stereochemistry. And then that byproduct now that's a carboxylic acid. So that mechanism shows you that it's a syn addition. It's synchronous because you're forming both CO bonds at the same time. And then it can do it from the other face as well, so that's how it produces the enantiomer. Any questions? So let me just see where we're at real quick. So we have about 15 minutes left. We're definitely not even halfway through. I hate to rush things, but we'll spend a couple minutes on why epoxides are important, but then I want to get to probably what we'll end up with. The last reaction here is hydroboration oxidation. So why are epoxides important? So when we look at that three-membered ring, we see that all of the atoms are sp3 hybridized. They should achieve a bond angle of 109.5 based on sp3 hybridization. You can see that because it's three atoms, it clearly doesn't do that right. You've taken this normal bond angle, you've compressed it now down to about 60. So remember, for a triangle, the internal angles all have to add up to 180. So we can say that those three angles are all 60. There's quite a bit of angular compression, which is strain, and strain means reactivity. So epoxides are used as reactive coupling partners, and we can do that under acidic or basic conditions. When we examine each carbon of that ether, let's classify it as if the oxygen were part of an alcohol. So we would say that that oxygen would be a secondary alcohol. This one would be tertiary. So that's as if you were just popping the ring open, and whatever carbon gets the OH, you classify it as an alcohol. So 1 is tertiary, so that eliminates A and B. 2 is secondary, so that eliminates D, so we're at C. So tertiary, secondary. Remember the reactivity trend for SN2? So methyl reacted faster than primary, primary faster than secondary, and tertiaries were unreactive. SN1 was the opposite. Tertiary is the greatest, primary not so much. So by classifying those carbons, then depending on what the reaction conditions are, is it going to be SN2 or SN1, we can see where the reaction is going to happen. So say we take our epoxide, we're going to treat it with acid, so hydronium ion. Hydronium ion is an acid. Therefore, the epoxide has to act as a base. It's going to get get protonated. So that will lose water. That oxygen's protonated. So remember in the SN1 mechanism, when the leaving group ionized, it formed a carbocation. We're going to ionize that, one of those CO bonds. But the leaving group, it's not leaving the molecule. It's just breaking a carbon-oxygen bond. So we can do that two ways. If we ionize it that way, how would you classify that carbocation? So there's the carbon, sp2 hybridized, p orbital, 1, 2, 3 carbons, so that's tertiary. Or we can ionize it the other way. Now when we classify that, we see it's secondary. So under acidic conditions, it's going to ionize to form the most stable carbocation. So it's going to go by choice A. So we use the carbocation stability trend, tertiary greater than secondary greater than primary. So acidic conditions proceed through carbocation intermediates. That's what we evaluate. And then basic conditions follow the SN2 trend. So it's going to run the opposite way. So if we continue that acidic conditions on, so we have H3O plus and water, what is the major product from that? And we're going to track that with the blue and red oxygens. So because that oxygen's on the top face, we can eliminate any possible responses with the blue oxygen on the bottom, so C is out. And then we said it was ionizing this way, so the blue oxygen has to be on carbon 2. So we can eliminate choice B and D, and we would end up as A is the correct response. So a hydroxyl group is called an alcohol. We have 2 of them in there, and we use that relative nomenclature to call this a 1,2 diol or a vicinal diol. Any questions? So there's the summary of that. Under acidic conditions, opening with acid and water, we can end up with a 1,2 diol. Now, if we're under, I'm calling it basic conditions or nucleophilic conditions, we're considering now the SN2 mechanism. We're going to use that rate of class. So methyl greater than primary, greater than secondary, greater than tertiary. And if we have a nucleophile, remember the trajectory has to be 180 degrees opposite the leaving group. The leaving group is the CO bond. The O doesn't leave the molecule. It just leaves from that carbon. When we classify tertiary versus secondary, we can see that the nucleophile should attack that carbon due to sterics. And therefore, that bond will have to break open. So the alcohol now is going to end up on carbon 3. So that produces a tertiary alcohol for that substrate. So this specific example of that, how do we recognize that it's SN2? We have a strong nucleophile, Na plus, Cn minus, acetone, it's polar and aprotic. That leads us to believe it's SN2. We then classified those as secondary and tertiary. It attacks Roman numeral 2, so choice B. That's how the ring's going to open. Any questions? All right, so I'm gonna suck up the last 5 minutes here and use them to my advantage. So as I said, we're obviously not getting through everything, but I mean, you have these notes. The other reactions are covered in screencasts. If you go onto YouTube, you can look at fall 2024. There's screencasts covering the rest of this material. But I do want to cover this one because it's a well-known reaction. It's called hydroboration oxidation. And the reason it's important, it was recognized with a Nobel Prize in 1979. So Brown at Purdue University helped apply these borane reagents to alkene addition reactions. And so borane itself is BH3. And when you look at that central boron, how many substituents does it have? So it has 3. So H, H, and H. So 3 times 2 electrons, that's 6. And for this class, we're dealing with the octet rule, right? So it's electron deficient. That means it has an empty p orbital. So borane is a Lewis acid. So BCNOF. So in that group, all of those elements end up being tri-coordinate. So an electron deficient reagent is a Lewis acid. The p orbital is empty. And we said that there's 2 electrons in a pi bond, right? Those 2 electrons can fill that empty p orbital. So it's a Lewis acid, Lewis base reaction. These other reagents, what you see is you're maintaining one of the boron H bonds, but then you're just substituting with some carbon stuff. And the reason for that is if you look at those groups, they're pretty big, and that's going to help with the regiochemical issue, because now you're adding H and B across the alkene. So which carbon gets H, which gets B? So real quick here, here's the electrophile, BH3. Notice in the product, there's no boron, right? So it's a two-step process. You do an addition of the borane, and then this should read step 2. You have these basic conditions of sodium hydroxide, hydrogen peroxide. That does an exchange of boron for oxygen. So you see in the major product, you end up with an alcohol. The intermediate from step 1, there was a boron there, and that boron got swapped out for an oxygen now. So hydroboration oxidation gives you an alcohol, but as compared to that hydration reaction, one of the first ones we saw on Monday, this is now lesser substituted. So the major product is now a secondary alcohol. So if you go back through the notes, the minor product of this, which is the tertiary alcohol, that was the major product from hydration. So hydration and hydroboration give opposite classes of alcohols through the electrophilic addition mechanism. So unfortunately, we are out of time, and again, Monday, Wednesday classes are a little bit more compressed. There's really not the same amount of time in the semester as a Monday, Wednesday, Friday. So unfortunately, we didn't get to everything.